Good morning, students. So today's class we are going to study about the least mean square adaptive filter. So before going to the LMS adaptive filter, first of all we will see what is an adaptive filter. So adaptive filter is the filter which automatically adjusts the weights according to the input signal. That is called adaptive filter. And if you see the difference between the adaptive filter and the normal filter, like a classical filter, so if you see the classical filter like low pass, high pass, band pass and band stop. So these are frequency selective filters. If you consider the low pass filter, it will allow only the low frequency components to pass through and does not allow any high frequency components to pass through. It completely attenuates the high frequency. That is the characteristics of a low pass filter. And when you consider the high pass filter, it will allow only the high frequency components to pass through. It completely attenuates the low frequency. That is the characteristics of a high pass filter. So that's why these filters like low pass, high pass, band pass and band reject filters, these filters we call it as classical filter or a frequency selective filter. Okay. So that's why suppose if the signal is buried with some noise or if the signal is added with some noise, in that case we want to extract the signal from the noise. Adaptive filter is the best option because adaptive filter it will adjust the weights according to the input signal and it will reduce the noise and produce the output. So that is the advantage of the adaptive filter. So in the adaptive filter, so now we are going to study about the least mean square algorithm. So LMS algorithm. So in this, what are the components involved? Here, some of the components involved are we need a reference input, variable gain, and the multipliers we call it as weights, and adaptation algorithm is very much important, and the input signal we call it as a primary signal. So any kind of adaptive filter you need a primary signal and a reference input. Two inputs are required, primary input, reference input. Then multipliers called weights, variable gain and adaptation algorithm. So these are the requirements of the LMS adaptive filter. Now, in this LMS adaptive filter, we have three principal components. So those are adaptive linear combiner, adaptive noise cancellation, and line enhancement. So these three are the important principal components. So one by one, we are going to study now. First, what is the adaptive linear combiner? So here we call it as a non-recursive adaptive filter. That means not having any feedback. That's why it's called as non-recursive. And if you see set of inputs, which is called as x1, x2, xl. So it is sent to a variable weights w0, w1, etc. till wl. So now this inputs multiplied with the weights and then it will go into the summation, which is called adder. So like that, how we can represent y as x1 into w0 plus x2 into w1 plus etc. xl into wl, like that. That is the response. Y is called as a response. So x1, x2, xl are nothing but set of inputs. Y is are called outputs, and this w0, w1, etc. wl is called weights. Okay. So now, if we want to represent a single input, how we can represent as xk equal to xk, xk minus 1, that is the previous sample with the delay of 1, xk minus 2, the previous sample is the delay of 2 seconds, etc. till xk minus L, the transpose. Now, if you want to represent the multiple inputs, how we can able to see represent in terms of x0k, x1k, x2k, x3k, etc., xlk, the whole power transpose. Now, if it is a single input response, how the response will be output yk equal to summation L equal to 0 to L, WLK is the weights, x of k minus L is the input. And if you have the multiple input response, in that case, the response is yk equal to summation L equal to 0 to L, WLK into xkl. Okay. So in a simplified matrix form, how we can represent as yk equal to xk transpose wk, which is equivalent to either we can write it as xk transpose wk or wk transpose xk. Okay, and simply the yk can be expressed as, when you expand this, we can expand it as x0 into w0 plus x1 into w1 plus x2 into w2, etc. So now if you see in this LMS adaptive filter, the inputs, set of inputs like x1, x2, xl till xl, it is multiplied by the weights, and this input multiplied by the weights, it's get added in the adder, and you are getting yk as an output. That is called actual output. Now we have a subtractor here. In the subtractor, another input to the two, there are two inputs to the subtractor. One input is called D, another input is from yk. What is D? D is nothing but the desired response, and yk is nothing but the actual response. So now the output which is obtained is error signal, we call it as ek, which is nothing but dk minus yk. When the error is 0, the signal will be taken as such. When the error is maximum, then it will be again fed back to the LMS adaptive filter. That is the concept in LMS adaptive filter. So now, according to the LMS adaptive filter, we need to find out the mean squared error. So for that, let us consider the performance function. The performance function here is yk equal to xk transpose w, which is, or we can express it as wk transpose xk in either way. Now the error signal ek equal to desired response minus the actual response, dk minus yk. So we are going to substitute the yk expression here in this place as dk minus xk transpose w, or we can write it in either way, dk minus w transpose xk in either way. Now we have to square the error. When you square the error, it is ek squared equal to dk minus w transpose xk, this whole square. This terminology we are going to use this expression, we are going to use it and square it. So it is in the form of like a minus b the whole square. When you expand it, how will you expand? It is a square plus 2ab plus b square. Now a square is nothing but dk. So dk square plus 2ab is minus 2 into dk into xk transpose w, plus b squared is nothing but w transpose xk. This we can express it as w transpose xk and w into xk transpose in that way. So now we are, after squaring it, we are going to apply the expectation over this. Expectation of ek squared equal to the entire expression, we are going to apply expectation or mean. E of dk squared plus w transpose into, to the xk and xk transpose, we are applying the expectation. The w and w transpose, we are kept it outside. Minus 2 into expectation of dk into xk transpose w. Let us mark this as equation number 1. Next, in this equation 1, this xk and xk transpose, no, this expression is called as a correlation function, autocorrelation function. We can represent in terms of r. R equal to expectation of xk into xk transpose. Let us consider this R as equation number 2. The next step, we just expand this E, xk and xk transpose. When we expand this by substituting the value for k like 0, 1, 2, 3, etc., you will be getting x0 k into x0 k. We can represent it x0 k squared. And here x0 k into x1 k and x0 k into xl k till xl k. Like that, we are expanding this equation number 2 and represent in terms of matrix form. Okay. Next, from the equation 1, you're taking this dk into xk transpose. That is expectation of dk into xk transpose. We are taking it and marking it as rho. And when you expand this, it will be dk is kept as such. This xk, we can represent x0 k, dk into x1 k, dk into x2 k, etc. dk into xl k, the transpose. Now, let us mark it as equation number 3. So, you have to substitute equation number 2 and 3 in this equation 1. So, we can express in the short form. So, when you substitute it, we will be getting the mean square error as expectation of k squared equal to expectation of dk squared plus w transpose into r. This expression we call it as r into w minus 2 into rho transpose w. This one we can call it as rho. So, rho transpose w and mark it as equation number 4. The next step is we need to find out the minimum of equation number 4. So for that we need to calculate the gradient of the squared error. So the gradient is nothing but ultimate difference here, differentiation of with respect to the mean squared error. So we have to differentiate this equation 4 with respect to the weights. So partially we have to differentiate. That's why delta equal to dou xi by dou w. With respect to the w weights, we are going to partially differentiate it. So when you differentiate this expression equation 4, the first term will be 0. In the second term, it is like a w squared. When you differentiate, it is 2rw. And second term will be minus 2 rho. So you will be getting the equation like this, and we have to equate it with 0. So when you equate this equation with 0, you will be getting the final expression as w star equal to r inverse of rho. And this one, w star, we call it as optimal weight vector. And this equations, we call it as Wiener-Hoff equation. Now, after obtaining this Wiener-Hoff equations, we have to substitute in equation 4, which is equation 4. This is this one. So, in this place, in the place of W star, we have to substitute R inverse of rho. Then, the next step, we have substituted in the place of W, wherever W, we made it as W star. And we have substituted this Wiener-Hoff equation here. So, the equation is, in order to find out the minimum error, so this is the equation. So now in this equation, in the place of W star, we are replacing with R inverse rho. So like this. And then we need to simplify this. Now when you see the first term will be remain as such, expectation of dk squared plus R inverse of transpose. R inverse of transpose is nothing but the R inverse itself. And R into R inverse is nothing but 1. This will get cancelled. Then rho transpose into rho minus 2 into rho transpose R inverse rho. These two, when you subtract it, simplify and subtract it, we will be getting minus rho transpose R inverse of rho. And again, this R inverse of rho, we can mark it as W star. So this is the minimum error we are getting. Expectation of dk squared minus rho transpose W star. So according to the least mean square filter, here we are following the steepest descent method. According to steepest descent method, so here in the data points, we used to find out the gradient, and whichever is the lower one, we used to see, and such that the error is minimum. So now we are taking the error signal Ek, so which is equal to dk minus xk transpose wk. So you are going to square that error and estimate the minimum error. So here what we are going to do, we are going to partially differentiate the weights with respect to the Ek square. So this we can, in this equation we can represent as 2 into Ek, dou Ek by dou W naught, etc. dou Ek by dou WL. So after differentiating, we will be getting this. So now dou Ek by dou W naught, with respect to Ek, when you differentiate this weights, you will be getting Xk minus Xk. So the next is according to del K transpose, it is minus 2 into Ek Xk transpose. This is what we get. Now the weights are adjusted in the direction of gradient of each steps. The new weights is represented Wk plus 1. This is equal to the old weight Wk plus new into minus delta K. Minus delta K cap is nothing but this expression. This we are substituting here. After substituting, we are getting the new weights as old weight Wk plus 2 into new, which is the learning rate parameter, and Ek is the error signal, Xk is an input signal. And also new is controls the stability and rate of convergence of the algorithm. Okay, so this is the LMS adaptation algorithm. The new weights is determined by old weight plus twice the learning rate parameter into the error signal into the input signal. Now, what is the necessary and sufficient condition for convergence of this learning rate parameter new? So, it will converges from 1 by lambda max to 0. That means lambda max is nothing but the largest eigenvalue of the correlation matrix R. Okay. So this is an adaptation algorithm. Now when you see the block diagram, this is the block diagram of an LMS adaptive filter in which you can able to see the inputs with a delay element. It is multiplied with the weights and given to the adder. So you can see x1 with the delay, it is multiplied with w1 and given to the adder, like that. X2, W2, it is given to the adder. And then you have a subtractor. One side to the subtractor is the desired input, another side is actual output. and this will produce the error. When the error is zero, you will be taking it as an output signal. When the error is maximum, it will be fed back to the adaptation algorithm so that it will adjust the weights according to the input signal. So this is the adaptation algorithm. It is Wj plus 1 equal to Wj plus 2 into nu epsilon j into xj. So you can able to see from the adaptation algorithm, the points are going to each weight vectors. So this is a LMS adaptive filter. Now this LMS adaptive filter, it is used in many applications like cancellation of power line interference in ECG, extracting the maternal ECG from fetal ECG, and then cancelling the donor heart interference from the um, recipient heart. So like that, for many applications, this LMS adaptive filter is used. Okay. So thank you all of you.